So all of those 11 were not detecting the payload at all. They were detecting the heap spray or the memory corruption JavaScript instead of the payload. So I think after we've added all these options together, and we still have 11 left, all those 11 were detecting other JavaScripts and not the payload itself. Okay. So we do a concat on the actual code. We end up with 1. And on the heap spray and the memory corruption code, we do a concat on that. We end up with 1. We do an injection on the shellcode, or the payload, and concat on the actual code. We end up with 0. Okay? So before this, all of this, we were manipulating the shellcode or the payload. And that brought us down to 11. But manipulating the actual heap spray or memory corruption JavaScript brought us very quickly down to 1 or 0. Random bars plus injection plus concat, also 0. However, VirusTotal runs the command line version of Antivirus. These versions are typically for vendors like us or for network vendors, email servers, load balancers, web caches, what have you, any kind of device that wants to have antivirus capability. And these console versions are actually very weak. The desktop version is much stronger. The reason is because the desktop version can monitor the host environment. So it can hook into browsers. It's easier to get the raw form of exploit, because if your browser decrypts the raw form out, then if I'm monitoring everything that your browser is doing, if I'm hooking into the JavaScript engine, then I can get the raw form. And then I can also do behavior analysis, because, for example, I can do buffer overflow analysis. If you have segments of executable code in data segments, for example, that's very obvious that it's a buffer overflow. And we can also monitor for download to file behavior. So this is a test on some of the using some of the bigger antivirus vendors. Didn't really list out the names, but you can guess. We used to give a lot of talk in Asia, and they weren't particularly happy when we list out the full names. And these are the algorithms that we used. So plain, for example, 2 antivirus didn't even catch the plain, so that wasn't. But right here you see this antivirus didn't catch anything but cache concat code, because they just figured that if it concatenating a lot of strings, then that's probably malicious, right? So that's a heuristic that worked for them. While for this vendor, it worked. All of our manipulation against the shellcode didn't bypass them, but once we started to concatenate, to obfuscate the other parts of the JavaScript, we actually got a bypass. And for this one, this vendor was very, very good. It went on to the last 2, which is injection against shellcode, concatenating the shellcode, and also fingerprint. So let's do a demo. Okay, so let's start our Drivesploit again this time. Let's use some parameters. So I want to use random variables. And I also want to use, I want to also concat the shellcode. sorry, true. And I also want to obfuscate using concat the rest of the JavaScript. Exploit. Start the exploitation process. Go into our VM. Let's just link directly to zcrack. Okay, so let's try clicking on remove. It's still detected after 3 options set. But although we click remove, actually the heaps array is still going on. It's not effectively really killing the exploit. And so as you can see here, a session started in interpreter, meaning that our VMs connected back to us. So this is the VM. And so let's connect to this session and list the processes. We can list the processes. We see Internet Explorer listed as 3092. So let's just kill that for them. And that kills the VM's Internet Explorer. And so we have full control over this VM, although the antivirus did alert, didn't kill it, but we don't want it to alert, right? We want to completely bypass it. This is one of the best ones for drive-by download detection already, by the way. So this time, let's set. We still want to use random vars. And this time, let's use injection for the shellcode. Insertion. This injects arbitrary commands, arbitrary strings. Oops. Doesn't matter, actually. And let's use concatenation for the rest of the JavaScript. Exploit. See what happens. This time it didn't alert. With antivirus desktop versions that has behavior monitoring or HIPS, host-based intrusion prevention systems in place, sometimes it's a bit of luck. For example, if you're doing heap spray for too long and notices that something's going on and you're allocating too much memory, it may alert. But in this case, it hasn't alerted. And we are with a new interpreter session. Again, let's kill the Internet Explorer for it. Here we go. Okay, so that's the demo for bypassing desktop versions. And that one was listed here, as you can see. Not very easy to bypass. And then we add another section. This vendor is very interesting. It appears to be one of the vendors that really properly implemented HIPS, host-based intrusion prevention system. And so there are 2 columns. So, for example, when we dump these exploits to a bare HTML file, and we ask it to scan the file, here's what happens. It doesn't have a lot of signatures, and it's not very good as these guys. These guys, it doesn't matter. These guys over here, actually, it doesn't matter whether you're loading content from a web server or you ask it to scan the bare HTML. It's some heuristics and everything put together, and they'll just detect. But for this vendor, if you're asking to detect static HTML, it doesn't have a lot of signatures. But when your browser loads and it's actually doing heap spray and it's trying to corrupt the memory, it detects all the time. And we'll tell you that. But however, it also has sometimes it has false positives. When you run commercial programs that are packed, it also alerts you. So that's a drawback. Okay, finally, last technique, behavior-based fingerprinting. So if we submit a behavior-based fingerprinting Drivesploit to a detection like WebAwet, it doesn't detect anything. But there's actually malicious JavaScript. What happens is, for example, when you use Mozilla and you alert it out, it alerts nothing. But when you use the correct browser that we're trying to exploit, it alerts the actual script. What happens is, here is browsers actually have very different implementations from each minor version to each minor version. And so we have implemented code that correctly fingerprints browsers based on these minor differences. Parser differences, CSS rendering differences, JavaScript engine grammar differences, for example. And so, it's this, we've developed code that can very precisely fingerprint which browsers are actually running the piece of JavaScript. We've implemented these functions. So use browser features as and then each checker actually generates 1 bit of the key. Okay? But however, each checker, every time when we serve the Drivesploit, the checkers are randomized. So bit 1 isn't always going to be the same checker. Okay? We randomize the order, and then we generate all the JavaScript checkers, and then we'll, of course, obfuscate the JavaScript. And then finally, you can use an option to set. For this Drivesploit, I only want IE6 to be able to decode it. Okay, then we will encode it. We'll randomize the checker orders. We'll generate these checkers for you, and then we will know what these checkers results are in IE6, and then we will generate the corresponding key in advance for you, and then we will encrypt our entire JavaScript using this key. So the only way for browsers to be able to correctly decode this is if it's actually running on the correct browser. Any type of automated detection, JavaScript engines, what have you, would all fail. And it's very hard for security researchers to analyze. And we've encountered quite a few of these with very fancy encryption algorithms, mostly in targeted attacks. So it defeats most automated detection mechanisms. We can try brute forcing the key, but then there's actually, you can put a time to it. We don't have time to explain this, but it's actually very hard. Because I can first serve you something to decrypt. You have to decrypt, give me the key first, and then I give you the actual script. And this key is invalidated after, for example, 2 minutes. So unless you can brute force in 2 minutes' time, otherwise it's not going to work. So why not antivirus? Why is it so hard for antivirus to detect the drive-by download threat? Well, antivirus is designed to install on desktops and notebooks. So on desktop and notebooks, there are a lot of very complicated behaviors, a lot of apps, a lot of heterogeneous apps installed, and it's very resource constrained. And therefore, antivirus and gateway vendors typically rely on signature-based pattern matching technologies that are lightweight and accurate. So for example, antivirus typically operates under the